In our last class, we started the nodal analysis algorithm in which you defined voltage variables at the various unknown nodes in a circuit, and then you used Kirchhoff's current law to solve for those voltage variables. So far, we looked at just the simplest case, where we only had one voltage source and it was connected to ground, so we knew the voltage at one of the nodes already, and then we used simple KCL equations to find the voltages at the other nodes. Today we're going to extend that by looking at more complicated cases. The first case we're going to look at is this circuit here. So if you look at the circuit, the first thing you note is rather than having just one voltage source, we have 4 different voltage sources. So that itself is going to make it a little more complicated. But let's see how we would tackle this problem. So the first thing we look at is we notice that we do not have ground defined anywhere, so we have to define ground. So let's look at our different nodes. We have a node down here. We have a node here. Big node up here. One more here. And we got to be clever here with how we signify these last couple nodes. One node there. And one node here. So we have a total of 6 different nodes. Now we need to decide where to put ground. Remember, for the algorithm that we've learned so far, the voltage sources have to be either grounded or connected to another voltage source connected to ground. Well, turns out, if we put ground down here on the yellow node, this 4-volt source is grounded, which means we know the voltage at the light blue node. That's a 4-volt source, and notice the plus is on the yellow side, so that means that the blue node is 4 volts lower than the yellow node. So the voltage at the blue node is actually negative 4 volts. The 6-volt source is not connected to ground. However, it is connected to that 4-volt source, which is connected to ground. So this does not violate the requirements for this algorithm. This also means that we know the voltage at the green node. The 6-volt source says that the green node is 6 volts higher than at the blue node. So if the blue node is at negative 4 volts, the green node is at plus 2 volts. Now you look at the 12-volt source. That is also not grounded, but it is connected to the 6-volt source, which is connected to the 4-volt source, which is connected to ground, so that also does not violate our algorithm. And that 12-volt source says that the green node is 12 volts higher than the yellow node with the red dashes on it. So if the green node is at 2 volts, the yellow node with the red slashes is at negative 10 volts. Finally, that 2-volt source itself is not grounded, but it's connected to the 12-volt source, which is connected to the 6-volt source, which is connected to the 4-volt source, which is grounded. So once again, that does not violate our algorithm. And that 2-volt source says that the yellow node with the red slashes is 2 volts higher than the green node with the red slashes. So if the yellow node with the red slashes is at negative 10 volts, the green node with the red slashes is at negative 12 volts. This combination of 4 voltage sources, each connected to each other, is called a tree of voltage sources. So if you go back to the algorithm, let's go back a few pages here. And the key phrase in this algorithm is in step 2a, or a path of voltage sources leading to ground. And that's exactly what we have in this example here. We have a path of voltage sources that do lead to ground, and so we can apply this algorithm. So there's one node left, and that is the pink node. This node we do not know the voltage at. There's no voltage sources connected to it, so it is a variable. We're going to call it Vx. So the first part of this problem is to set it up by examining every node and determining whether we know the voltage. If so, we write it down, or if we don't know the voltage, we write it as a variable. The next step then is to write a KCL equation at every node for which you do not know the voltage. There's only one, this node here. So we're going to write KCL at that node. Basically, we're going to say that this current plus that current plus that current equals 0. So KCL at the Vx node is what? Current going in this direction, that's a current through that 2 kilo ohm resistor. Remember, the current through the resistor is the voltage at the coming from point minus the voltage at the going to point divided by the resistance. So that current is Vx minus 2 volts divided by the resistance, 2 kilo ohms. Current going in this direction, current going down, is what? It's Vx minus 0, because the other end is ground, over 2000 ohms. Current going to the right is the voltage at the coming from point, Vx, minus the voltage at the going to point, which is negative 4. You got to be careful about this. You have a double negative. Vx minus negative 4, once again, over 2000 is equal to 0. That is the only KCL equation that we need to write because that Vx node, that pink node, is the only node that we did not know the voltage at. We have one equation and one unknown. We can solve for Vx, and you get Vx is equal to minus 2/3 of a volt. So we can write that down. So at this point, we have now determined the voltage at every node in the circuit. And notice because we had all of these voltage sources, most of these were determined even before we wrote a single equation. The only one we really had to write the equation for was the pink node to solve for Vx. We have not finished the problem though, because the problem did not ask us to find the voltage at every node. The question asked us to find what? The current Ix and Iy. So now that we know the voltage at every node, we can now use things like Ohm's law to find whatever we're looking for. So let's look at Iy first because that's the simpler of the two. So to find Iy, that is the current through this 1 kilo ohm resistor. Remember, the current through a resistor is always the voltage at the coming from node minus the voltage at the going to node divided by the resistance. So Iy, the voltage at the coming from node is that node, 2 volts. The voltage at the going to node is negative 12 volts. So it's 2 volts minus negative 12 volts divided by the resistance 1000 ohms. You work that out, you get 14 milliamps. So Iy is 14 milliamps. We were then asked to find Ix. Ix is the current through this 2 kilo ohm resistor on the bottom left of the circuit. Specifically, it is the current going up. So what is Ix? It's the voltage at the coming from point, that's the voltage down here, which is 0 volts, minus the voltage at the going to point, that's what we just solved for, that is negative 2/3 of a volt, divided by the resistance, 2000 ohms. So 0 minus negative 2/3 divided by 2000, you work out that math, you get 1/3 of a milliamp. So we see that Ix is 1/3 of a milliamp and Iy is 14 milliamps. So once again, this example was slightly more complicated because you had more voltage sources, but because they were all tied together and one of them was tied to ground, we were able to solve for the unknown voltage, in this case Vx, and from there we were able to find all of the currents. So the next complication we're going to look at is dependent sources. So when you have a dependent source, you basically just have a couple additional steps. The first thing that you want to do, when you write your equations for your circuit, you treat the dependent sources just as if they were independent sources. If it's a dependent voltage source, treat it like an independent voltage source. If it's a dependent current source, treat it like an independent current source. But the other thing you need to do then is once you set up all your variables, you look at the controlling variable. For example, if it's a voltage-controlled current source, that controlling voltage is your control variable. What you want to do before you write your KCL equations, you want to express the dependent source control variable in terms of the node voltages, and then substitute that expression into the KCL equations that you're writing. So in other words, you want to get rid of your dependent source control variable. The only variables you want to keep are the node voltage variables that you created when setting up the problem. And we'll see this with an example now. So this circuit, notice ground is given, so we don't have to worry about that. Let's identify all of our nodes. We have our ground node here, put that in yellow. Node there. We have a node there. And we have a node there. So we have 4 nodes. So now you look at every node and determine whether you know the voltage or not. So the node on the left, the green node, it's connected to a current source and a couple resistors. We do not know its voltage, so I'll give it a variable. I'll call that V1. The blue node is connected to a dependent current source and a couple resistors. Once again, we don't know the voltage there. We're going to give that another variable, V2. Third node, the pink node, is the tricky one. It's connected to a voltage source, and if it was an independent voltage source, let's say 10 volts, we would know that the pink node was a voltage of 10 volts. It is a voltage source, but it's a dependent voltage source, so we don't quite know the voltage yet, but we don't treat it the same as the green node and the blue node because it is a voltage source. So its value is going to be 2Vx. So we're treating it like an independent source, but we're just giving it a value of 2Vx now because that's the value of this dependent voltage source. So the first thing you do when you have a dependent source is you treat it just like an independent source when you set up your variables. Now here's the important part. We want to re-express the two control variables, which are what? The two control variables are the Vx variable, which is that there, and the Ix variable, which is that variable there. We want to re-express Vx and Ix in terms of V1 and V2. So we want to re-express Vx and Ix in terms of V1 and V2. In other words, as I said before, we want to get rid of the Vx and Ix variables. The only variables we want to deal with are V1 and V2. So let's look at Vx. Vx is the relative voltage across the 4 ohm resistor on the top of the circuit. Remember, a relative voltage can always be expressed as a difference between two absolute voltages. So Vx equals the voltage at the left end of the 4 ohm resistor minus the voltage at the right end. So Vx is equal to V1 minus V2. Why is it V1 minus V2? Because the Vx variable was defined with the plus on the left. If the plus was on the right, Vx would be V2 minus V1. For Ix, we have to use Ohm's law. The current through the resistor is the voltage across the resistor divided by the resistance. The voltage across the resistor is the voltage at the left end minus the voltage at the right end. So from Ohm's law, Ix is the voltage at the left end, which is this variable V1, minus the voltage at the right end, minus 2Vx, over the resistance, 4 ohms. Remember, we want to express Ix only in terms of V1 and V2. So now what we need to do is we take this expression for Vx and plug it in there. And so we get that Ix is equal to V1 minus 2, V1 minus V2, all of that over 4, or negative V1 over 4 plus V2 over 2. So this was the added step that we needed to deal with because we have the dependent source. Once you express our two controlling variables, Vx and Ix in this example, in terms of the node voltage variables that you want to keep, in this example V1 and V2, we're now ready to write the KCL equations. So the equations we need to write a KCL equation for this node, the V1 node, and for the V2 node. And you might say, well, what about that middle node? We don't know that voltage. That's true, but that is a voltage source, so we don't write a KCL equation there. Remember, we treat that dependent source like an independent source. The only caveat is we had to express our variable Vx in terms of V1 and V2. So the only KCL equations we write are the ones for the green node and the blue node. So KCL at the V1 node, basically we're saying that this current plus that current is equal to 0. So the current going down is what? Minus 3 amps. Current going up is the current through the 4 ohm resistor. It's the voltage at the coming from point minus the voltage at the going to point divided by the resistance. So it's plus V1 minus V2 over 4. The current going right through this other 4 ohm resistor is what? It's V1 minus 2Vx, but remember Vx itself is V1 minus V2. All of that over 4 ohms. The sum of those three currents has to be 0. You solve, and actually this turns out that V2 over 4 is 3, or V2 is equal to 12 volts. So every once in a while you may find that you have an equation in two variables where one of the variables drops out and you can solve for the other one directly, and that's what happened in this case. That's not normal, but sometimes it can happen, and that actually makes your math a lot easier because you're going to see that you don't have two equations you have to solve simultaneously in two unknowns. So now let's look at the V2 node. So KCL at the V2 node is what? We're summing this current plus that current plus that current equals 0. So let's start with this top current. So the top current is what? It's the voltage at the coming from point, V2, minus the voltage at the going to point, V1, all over that resistance. Current to the left, current to the 1 ohm resistor, is V2 minus 2Vx, minus 2, and of course Vx itself is written as V1 minus V2, all of that over 1 ohm. Current going down is 6Ix, but we don't write Ix as Ix, we write it as 6 times minus V1 over 4 plus V2 over 2, and we sum all of that to equal 0. When you simplify the second equation, you get minus 15/4 V1 plus 25/4 V2 is equal to 0. Since we already know that V2 is 12 volts, you can solve for V1. You get V1 is equal to 20 volts. So at this point, we know that V1 was 20 volts. V2 was equal to 12 volts. What did the question actually ask for? It said, determine the voltage at every node of the circuit. So we're actually 2/3 of the way through because we know V1 and V2. We now can figure out the voltage at the pink node. Remember, that was the dependent source voltage. It was 2Vx, but Vx itself is what? Vx is V1 minus V2, 20 volts minus 12 volts, or 8 volts. So that means that 2Vx is 16 volts. That's our final node here. So at this point, we've now answered the question and found the voltage at every node in the circuit. So once again, dependent sources add a little wrinkle because we need to take care of these control variables and re-express them in terms of the variables we want to keep. The bottom line is the only variables you want in your final equations for nodal analysis are our node voltage variables, in this example, V1 and V2. So if you remember, when we looked at our first nodal analysis algorithm, we called that a type 1 circuit where all voltage sources were grounded. We said the current sources could be anywhere, but that if there were voltage sources, they had to be either connected to ground or connected through a path of other voltage sources to ground, as we saw in this example a few pages ago, right there. We're now going to look at type 2 circuits. These are circuits in which we have floating voltage sources. So a floating voltage source is one that is not grounded. That's one where neither end of the voltage source is either connected to ground nor connected to other voltage sources that are connected to ground. So this creates a problem because what happens is because you don't know the voltage at either end of those floating voltage sources, you need to write a KCL equation. But because you don't know the current through the voltage source, as we're going to see in the next couple pages, you can't write a KCL equation. So you need to write a KCL equation, but you can't write a KCL equation. That's going to give us a problem. So the solution to this, there are two ways. One is something called supernode analysis, which we'll introduce in this class. And then the other approach is a modified nodal analysis, which is used in some software such as SPICE or Multisim. We're not going to cover that in this course because the supernode analysis works just fine. But anyway, just so you understand what we mean by a floating source, let's draw a simple circuit here. So this voltage source on the left is grounded. One end of it is connected to ground. This voltage source over here is floating because neither one of its nodes is connected to ground, nor is it connected to another voltage source connected to ground. So if you had a circuit like this, we would call this a type 2 circuit, and we have to use this modified algorithm that we're going to be coming up with now. So before we come up with the algorithm, let's try to solve a circuit with a floating voltage source so we see exactly what the problem is. So here we have a circuit, and this doesn't look terribly different from the circuits we looked at before until we start trying to solve it. So let's start by defining ground. So we have this 4-volt source here, so we better put a ground connected to it to make sure it's grounded. Now let's look at every node. So we have our ground node right here. We have a node there, a node there, a big node up here. Let's make that yellow with red slashes. And let's make this node green with red slashes. So you have a total of 1, 2, 3, 4, 5, 6 different nodes. Now you look at every node and determine, do you know the voltage? Do you not know the voltage? Obviously the yellow node, you know the voltage. It's 0 volts, it's ground. The pink node is connected to a voltage source connected to ground. That 4-volt source is connected to ground. And so the pink node, the voltage is what? It's a negative 4 volts. Why is it negative 4 volts? Because of where the minus and the plus sign are in this 4-volt source. This 4-volt source is saying that the yellow node is 4 volts higher than the pink node. So the pink node needs to be at negative 4 volts. The 6-volt source is not grounded, but like that example a few pages ago, it's connected to the 4-volt source, which is connected to ground. The green node is 6 volts higher than the pink node. Since the pink node is at negative 4 volts, the green node is at positive 2 volts. Blue node is not connected to any voltage sources at all, so we certainly don't know its voltage, so we're going to give it a variable VA. Let's look at this 2-volt source on the right here. Do you know the voltage on the yellow node with the red slashes? You might say, well, it's 2 volts. No, it would be 2 volts if the green node with the red slashes was connected to ground. But it isn't. All that 2-volt source is telling us is that the yellow node with the red slashes is 2 volts higher than the green node with the red slashes. But we don't know what the voltage at the green node with the red slashes is, so the voltage at the yellow node with the red slashes has to be a variable. We're going to call it VB. Likewise, the green node with the red slashes, its voltage is 2 volts lower than the yellow node with the red slashes, but we still don't know what it is, so we need to give it a variable, VC. So because we don't know the voltage at VB and VC, that means we need to write KCL equations. But let's see what happens when we try to write a KCL equation. Let's start with a KCL equation at node VA. So basically we're saying that this current plus that current plus that current plus that current has to sum to 0. So KCL at VA, current through this leftmost 2 kilo ohm resistor is the voltage at the coming from point VA minus the voltage at the going to point, 2 volts, divided by its resistance, 2000 ohms. No problem there. Current through this 2 kilo ohm resistor is VA minus negative 4. You got to be careful about that. Divided by its resistance, 2 kilo ohms. No problem there. Current through this 1 kilo ohm resistor is VA minus VB over 1000. No problem there. Finally, the current through this 1 kilo ohm resistor is VA minus VC over 1000. No problem there. Some of those is equal to 0. No problem so far, so we're happy. Now let's look at the VB node. So if you try to do KCL at the VB node, it's this current plus that current plus that current is equal to 0. Current going down here through this 1 kilo ohm resistor is what? VB minus 0 over 1000. No problem there. What's the current through this 1 kilo ohm resistor? The voltage at the coming from point minus the voltage at the going to point divided by the resistance. No problem there. Plus, what's the current through a 2-volt source? Is the current through a voltage source 0? Absolutely not. Is the current 2 volts? No, that's a voltage, not a current. So we have a problem. We don't know what that current is. The sum of those 3 currents does have to equal 0, but we have no way to express that current. Likewise, if we try to write a KCL equation at VC, it's that current plus that current plus that current is equal to 0. Current going down is VC minus 0 over 1,000. Current going up, VC minus VA over 1,000. Current going to the left. Once again, we have a problem. We do not know what the current through a voltage source is. We have no way to express that. So this equation is true, but we can't solve it because we don't know what goes into this question mark. So we have a problem. And the problem once again is, because the voltage source is floating, we don't know the voltage at either end of the voltage source. So we need to write a KCL equation. But because we don't know the current through the voltage source, we can't write a KCL equation. So what do you do when you have a problem? Well, in the real world, what do we do when we have a problem? We call a superhero. Batman, Superman, Iron Man, etc. So in circuit analysis, you call a superhero. The superhero we call is supernode. So let's give him a little cape. So supernode is a solution to the problem of when you have a floating voltage source. Let's define what we mean by supernode and see how you could use that to get by this problem. So if you remember when we first talked about Kirchhoff's current law, we said that not only does the current leaving any node equal 0, but the current leaving any closed Gaussian surface, or which we also called a supernode, has to be 0. So we're going to use this concept now to avoid the problem of not knowing what the current through a voltage source is. So for example, if you look at the circuit on the left here, and I have a lot of the circuit just as a blue blob, but let's say we want to try to write a KCL equation at node V2. So KCL at V2, once again, the current to the left, pretty simple. It's V2 minus V1 over R1. The current to the right is V2 minus V3 over R2. But the current going down is that current through that voltage source Vx. We don't know what it is. So you cannot really effectively write a KCL equation at this node here. What we're going to do, though, is whenever we have a floating voltage source, we're basically going to draw an oval around it. We call that a supernode. Then when we go to write a KCL equation, rather than writing the sum of the currents leaving the node, we write the sum of the currents leaving the supernode. So now we're going to say that this current plus this current plus this current plus this current has to equal 0. Now that's a true statement because remember, the sum of the currents leaving any closed surface has to be 0. But what happens when we try to write a KCL equation at this so-called supernode? So KCL at the supernode, current to the left once again is V2 minus V1 over R1. We can do that. Current to the right is V2 minus V3 over R2. We can write that. This current on the bottom left is V4 minus V5 over R4. Hey, you can do that. This current down here is V4 minus 0 over R3. So what happens is because we use this supernode concept, we avoided the impossible problem of having to find the current through that voltage source. Instead, we sort of extended that node to make it into a supernode and then found that the current through the voltage source, this current going down this way, itself branched out into a current coming to the left and a current coming down. And that's basically what we're doing with the supernode analysis. And so this is going to be the idea behind solving these type 2 circuits where we have floating voltage sources. Whenever you have a floating voltage source, you're going to construct a supernode and do a KCL equation for the supernode. So how is that going to change our algorithm? So basically we start with our standard algorithm for the type 1 circuits, except in step 2 where we're looking at every single node and determining whether it is a known voltage or not, we're now going to have a couple different situations. If you have a voltage source, it's either going to be connected to ground or connected to other voltage sources connected to ground. This is what we saw before. So we saw this in type 1. But then in addition to that, we might have one or more voltage sources that are floating. For each of those, we have to create a supernode. So this is going to be a new step. As far as equations go, when we write our KCL equations, first off, we have our standard nodes that have no voltage sources associated with them. We can write standard KCL equations for them. But then in addition, whenever you have a supernode, you write a KCL equation for each supernode. But this introduces a problem in itself. Let's go back a page here. So if you look at this circuit here, we have two different nodes here associated with this voltage source Vx. We have this V2 node and this V4 node. So if you have two variables V2 and V4, you need two equations. But we only have one KCL equation to write, this supernode KCL equation that we have up on top here. So we have one equation, but we have two different unknowns. How do we handle that? We handle that by writing an additional equation called a source equation. Because the fact is that in this example, V2 is Vx volts higher than V4. Vx is going to be some number, 5 volts, 10 volts, 15 volts, whatever. So we also have what's called a source equation. Whenever you have a supernode, you also have a source equation, which is relating the absolute voltages on the two ends of the supernode voltage source. So in this case, the source equation is what? V2 minus V4 is whatever this value Vx is going to be. So this is the second added thing in this algorithm, is you have to write a source equation for every supernode voltage source. This bullet point down here I'm going to briefly mention, and then we're not going to talk about it anymore. So there is another approach. Rather than writing source equations, when you define your voltage variables, when you have a supernode, you can basically build the source equation right into the definition of the variables. Let me show you an example here. So suppose you have a situation, and this is just part of a circuit. Suppose you have a voltage variable V1 there, and you have a floating 10 volt source. You have a variable V2 here. So basically we'd have our supernode. And then the algorithm that I use, we have our source equation. We would say that V2 minus V1 is 10 volts. This is our source equation. An alternative way to handle supernodes when you make our variables, we have V1 here. We have this floating source, this 10 volt floating source here. Rather than introducing another variable V2, what we could do is just call this node at the right, we could call its voltage V1 plus 10 volts. We'd still have our supernode, and we'd still have to write our supernode KCL equations, that current plus that current plus that current plus that current is equal to 0, but we don't introduce another variable. Now this seems like it's actually better because you have one less variable to deal with. I personally find it a little confusing. I find it better to just define these voltages V1 and V2 and then write a source equation. Using this approach on the right actually yields fewer equations and fewer unknowns, which once again might seem like a good thing to do, but I find it a little confusing. So I prefer this approach on the left. So when I teach this, when I give the algorithm, when I do the examples, I'm going to use the approach on the left. If you want to dabble with the approach on the right and see if you prefer it, you're more than welcome to do so. Another point about supernode analysis is the location of ground may determine whether you even need supernode analysis. So look at these two circuits here. These two circuits are the same except for the ground location. In the circuit on the left, the ground is on the bottom. In the circuit on the right, the ground is this middle node. So let's try to analyze the circuit on the left. So we look at every node, a node there, a node there, a node there, and a node there, and determine whether you know the voltage at every node. So the voltage here obviously is 0 volts, it's ground. The pink node, the 12 volt source is connected between the pink node and the yellow node, so we know the voltage at the pink node has to be 12 volts. The 3 volt source connects the blue node to the pink node. If the pink node is at 12 volts, the blue node needs to be at 15 volts. So this is our path of voltage sources connected to ground, the 3 volt and the 12 volt source. The green node is not connected to any voltage sources. We do not know its voltage, so it's a variable V1. So basically we would have to write a KCL equation here. This current plus that current is equal to 0. One equation and one unknown. Circuit on the right is the same exact circuit, except we're defining ground differently. So we still have our 4 nodes. One node there, one node there, one node there, and this node here in the middle. But now, since ground is defined as this middle node, that is the known voltage. But now we look at these other nodes. Look at the blue node. Do you know the voltage at the blue node? It's still connected to that 3 volt source, which is connected to the 12 volt source, but we don't know the voltage at the end of any of those voltage sources. So this is unknown, so this is a variable. Make it V1. Likewise, the pink node. Yes, it's connected to a couple voltage sources, but neither voltage source is grounded, so that's also a variable V2. Yellow node in this case, once again, is connected to another voltage source, the 12 volt source, but because it's not grounded and the 3 volt source is not grounded, we do not know the voltage, and so this is also unknown, V3. So what happens in this example is you basically have these two sources together are floating. Because they're floating, this is now a type 2 circuit. So the circuit on the left is type 1. The circuit on the right is type 2. We need to write a supernode. And so let me erase what I just did there. So we would have to write a KCL equation basically summing up the current leaving the supernode there, 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 and there is equal to 0. So if we wanted to write this equation, the supernode KCL equation, is what? Current through this 3 ohm resistor is the voltage at the coming from point minus the voltage at the going to point over the resistance. Current through here is simple, it's 4 amps. Current through here is the voltage at the coming from point, V2, minus the voltage at the going to point, 0 volts, over 2 ohms. Current through the 6 amp source is negative 6 amps because of the current direction. Finally, the current through this 3 ohm resistor is what? It's V3 minus V1 over 3 ohms. And all of that sums to 0. And if you're astute, you would notice that that current and that current cancel. But nevertheless, we have one equation in 3 unknowns. You cannot solve one equation in 3 unknowns. Where are you going to get your other 2 equations? You can't write any more KCL equations, but what do you have? You have your 2 source equations. So you have 2 source equations. From the 12 volt source, we know that the pink node is 12 volts higher than the yellow node, so V2 minus V3 is 12. Likewise, from the 3 volt source, we know that V1 is 3 volts higher than V2. So the second source equation is V1 minus V2 is equal to 3. So what we see on this page is that if you're given the choice of where to put ground, sometimes putting ground in different places can make a big difference in how much work. Circuit on the left is 1 equation and 1 unknown. Circuit on the right is 3 equations and 3 unknowns. So choosing ground judiciously can greatly simplify your work. Once again, this is a type 1 circuit, easy. This one on the right is a type 2 circuit, a little more difficult. So in our next class, we will completely develop the algorithm for these type 2 circuits, and then we'll do some examples. Have a good day.